some more basic stuff, which might have already been sort of referred to at a more technical level in the past lectures, but I hope it's still useful. So remember where we closed at the end of last time was the statement of the Cobordism hypothesis. It said that n-dimensional framed TFTs in some target are the same as what are called fully dualizable objects of that target. And we had this funny definition that an object X is fully dualizable if you can sandwich it in some subcategory S prime, and you can ensure that S prime has all duals and adjoints. And we talked about what duals and adjoints mean, and they mean the same thing that you mean when you talk about a dual of a vector space or an adjoint of a functor. So of course I'm not going to even sketch the proof of the Cobordism hypothesis, but I think it's useful to explain why you would consider this dualizability notion with some pictures. Draw those pictures, and then we're going to start climbing David Ayala's mountain and going through our examples. Okay, so right. I want you to think of a picture of a rainbow. So we said that the graphical calculus for thinking about duals of vector spaces, so we might imagine a vector space and its dual, we have an evaluation, we have a co-evaluation, and the key compatibility between the evaluation and the co-evaluation, which essentially encodes just matrix multiplication, is that if I do the identity on the plus component, so I write plus disjoint union empty set. I do nothing on the plus component, and then I use the co-evaluation to create two pairs of opposite points, minus and plus. And then if I take one of those and I evaluate the plus and the minus here, so at this point right here in the middle, it looks like plus minus plus, plus minus plus. Then I evaluate here. Then I'm back down to a morphism to plus, and the key axiom that you ask for is that this is the same as plus. And the whole point is that, like, topologically, you just introduce a wrinkle. Okay. All right. So to motivate the higher structures that we want to see, I want to encourage you to think about adjoints of morphisms also using this rainbow picture. So here's here's the evaluation and the co-evaluation. I'm going to stop worrying about pluses and minuses just to not clutter the diagram. Here's an example of an evaluation that we had on some object. And here's its left adjoint. I wrote right adjoint last time, and someone corrected me. Thank you. Okay, so if these are morphisms in a two category, we're supposed to have this notion of the unit and the co-unit. And the units and the co-units are coming by taking the morphism and either writing the morphism after its left adjoint or the left adjoint after the morphism. And in both cases, what we're going to do is we're going to take that, just like we did here, we're going to trace out a rainbow. So this thing is just a rainbow that traces out plus and ends at minus. This is an upside down rainbow. If I trace this thing out as a rainbow, I get this picture. And you see it's a saddle. It's like the critical point on the torus, a little piece of the torus. And then to interpret that as a manifold with corners, I'm just going to pinch these corners up to make it nice and rigid. Okay. And so what this is, now this is a map from evaluation after its left adjoint to, and what is this? This is just the identity, because it's just straight bars. Those are the identity. So this thing represents the data that we've asked for, that we should have a co-unit for the junction. And then similarly, if we compose them in the other way and we did a rainbow, then we would get this picture, and we cinch that up to give us a torus. Okay. And then finally, the sort of stand-in of the Zorro axiom It's literally the same thing, but we just do it in one dimension higher. So here's the unit of the adjunction, so which corresponds to the co-evaluation. That's the sphere. But then I've done nothing on this side. So this is the identity.
The blue thing is very hard to see from here. I don't know, maybe you can...
Yeah, let me trace it over another color. Sorry about that. Yeah, I see what you mean. Okay, I can see it, yes. Okay, so let me trace over the blue thing in brown. You don't like that? Okay. So at the bottom here, we've got ev L. Okay, what did I do? I used the unit, which is like the co-evaluation before, to take, I leave ev L alone. I have the empty set here. I apply that, I get a circle. And now I break that circle up into two pieces. One is the identity here this is the identity on also on ev L. Here's ev. And then I use the evaluation, which is the co-unit for the adjunction. That's the saddle. I put this thing here. And then when I do that, I do nothing on this side. Yeah, so this picture is supposed to be exactly, well, the reflection of that. And then you just look at this thing and you see, aha, this big bulby thing, I can just push it in, and it just becomes a half cylinder. It just becomes the identity. Yeah, just like I took this bit of bulge and I moved it in, I just take this bit of bulge and I move it out. Okay. So that was a sketch of the proof that every, so what did we do? We started with an object. In order to even get started, that object had to have a dual. And then here I wrote its evaluation and co-evaluation, that's part of the duality data. And then I convinced you that topologically that data has an adjoint like this. And now if we would go in 3 dimensions, we would have a similar picture all the way up. And so so what we've said is that Cob n frame is fully dualizable. So if we're going to define a functor from something fully dualizable into S, well, of course, the image of this functor has to land in the fully dualizable part, because you just take all the dualizability data there and you'll just push it through. So that's the easy direction of the Cobordism hypothesis. And the hard direction is proving that once you've satisfied that sort of obvious criteria, that you can go the other way, that you've done everything you need.
David,
Yeah.
the left adjoint and the right adjoint should be the co-evaluation. It's always like...
Not exactly. So that's a good question. So the question is that this thing sure looks like that thing,
Yes.
but if you note, it's not quite, because like here I would have plus minus. In order for this picture to make sense here, I also have plus minus, whereas the co-evaluation has minus plus. Now, it's a good question. In a symmetric monoidal category, it is true that the left adjoint of the evaluation is just the fix to this. So there's an identity that says that basically this thing is equal to, well, this thing. So you can, so you were basically right. You just have to introduce a kink. But unfortunately, that trick is not going to serve you higher and higher once you go past the objects. You can't keep doing that. You do a lot of tricks like that, but it gets more subtle. Good. Okay. All right, so that's the end of the topology, and now I want to just start doing some algebra. And so we're going to start climbing the homotopy way, I guess, of David Ayala. Okay, so the first peak that we get to peak number 1. So we're going to let S be the category of vector spaces. I'm just going to work over a field C, which is characteristic 0 and algebraically closed. It's interesting to consider other fields, but some things I say will not be true. Okay. All right. So this is an easy exercise. So if we look at Z of a point, this is going to be some vector space V. And the first thing that you notice is that in order to have an evaluation and co-evaluation, V has to be finite dimensional. Indeed, let me draw it more carefully. So this is a figure 8. This is just a circle, but I'm being careful in the way that I was prompted to about pluses and minuses. This circle, so there's not really a singularity there. It's like that. This circle, when we just write out the formula for it, it's the sum of, so we first of all take the sum of a basis tensor, a dual basis, that's the co-evaluation. But then we evaluate this thing, but by definition of a basis and a dual basis, this is just the dimension of V. Okay, so an easy exercise is that to give a one-dimensional TFT, all you need to do is give a finite dimensional vector space. So I'll leave it as an exercise to prove the converse. Okay, so now let's go higher on the mountain. Okay, so there's two essentially equivalent pictures. I'll just pick one of them. So we can talk about certain kinds of K-linear categories, C-linear categories, like the kinds that were in Michaela's lectures, and they have a tensor product on them. So K-linear category, it's a category, just one category. Its HOMs are vector spaces. And there's a tensor product, which is just sort of the obvious thing. You just take the Cartesian product of the objects and you tensor the HOMs. Maybe a more concrete way to think about this, which I would prefer, is we could look at the 2 category, which I'll say now, of algebras in vector spaces. So what is this? So it's a 2 category. So the objects are just associative algebras. Okay. The slightly subtle thing is that the one morphisms are not homomorphisms of algebras, which would be your first guess. But if I have 2 algebras A and B, then the HOMs from A to B is itself now a category. It's the category of AB bimodules. Okay, and then the 2 morphisms become obvious. So HOMs, let's call those bimodules M and N, and then HOMs between N and N. These are just bimodule homomorphisms. So just maps between the bimodules that commute with the existing AB action. Yeah.
So you say we have these 2 things to consider. Is this the only 2 things that work, or are the only 2 things that we end up considering?
These 2? These are just 2 examples that I'm interested in expositing. There are many others. Yeah. Yeah. But these ones, there's a way to basically, these ones are basically the same in good settings. So that's all. That's the only reason I stated them both, just to say that in good settings they're the same. Thank you for that question. Okay. Right, okay, so now all we need to do is we need to start checking the dualizability. That's the game we're going to be playing this entire lecture. I give you a category, I tell you what its objects are, I'm going to start naming the evaluations and co-evaluations and just climbing up the ladder and seeing what we get. So a basic fact, I realize I should have been citing Lurie for a lot of this stuff. So Baez and Dolan stated the Cobordism hypothesis in a sort of general wish list sort of way, and Lurie had to write down precise definitions, and then he gave a sort of sketch of a proof. The proof had some gaps, which he acknowledged when he posted a sketch, and people are still working on it. But all of the sort of structure around it is due to him. I won't say his name all the time, but he's there everywhere.
The symmetric monodal structure here is still tensor product?
Yes, good. Yes, so if I have good, yeah. Thank you for asking. So here I told you what it is. Here it's if I have associative algebras A and B, it's an excellent question. I take the tensor product over the ground field, and then I just make that an algebra where A does its own thing and B does its own thing. Yeah. So it's like the disjoint union algebraically. Thank you. That's important. So good. And so in particular, thank you. So an A-B bimodule, therefore, is just the same as an A tensor B op module in that way, and that's an important observation, which I'll actually use right now. So, okay, given A, I have to tell you what the dual is, because I've said that every object is supposed to have a dual. The dual is going to be A op. Brilliant. Now, to say that the dual is A op, I don't get to just pick it. What I have to do is I have to pick it, and then I have to convince you that it has an evaluation and a co-evaluation that satisfy certain properties. But happily, we have such a thing. So the unit, this is duals. The unit in this category of algebras is just the ground field itself. And so now what is a evaluation? I'm supposed to give you a bimodule from A tensor A op tensor A. I'm supposed to give you a morphism from A op tensor A to the ground field. But now remember that this is not a homomorphism of algebras, but it's a bimodule. Okay. But having a C bimodule on the right, it just doesn't do anything because everything is enriched over C. So I have to give you an A op tensor A module, and what I do is I just give you A. So here's a picture. We have A, we have A, we have A op, and then the data that I need to give you is just A itself, thought of as a bimodule. And the Zoro axiom is just trivial. It's just something about the fact that when you tensor a module over the algebra itself, you do nothing. Okay, so the upshot is, and this is important, we'll come back to this, every algebra is one dualizable. Okay, I'll say that this is a very general thing that I'll explain. Okay, but now it gets more interesting when we talk about two dualizability. So now for two dualizability, what we need to do is we need to take this morphism and ask if it has adjoints. So that is, we need to regard A as an A op tensor A C bimodule, and ask if it has adjoints. Okay. Well, it turns out, so actually going back to the previous example, to say that it has adjoints on the right for C is just to ask that A is dualizable as a vector space. So the dualizability on one side, this is going to imply something very strong. This is going to imply that A is finite dimensional as a vector space. Okay, so we saw that like any algebra at all was one dualizable, but that in order to be, we're working towards two dualizable or fully dualizable, then we get a really strong restriction. It has to be finite. Okay, but then on the other side, what we're doing is we're looking at A op tensor A, and we're looking at how it acts on A. and we want this to be dualizable as well. But in general, if I have, so as an aside, if I have any algebra, call it B, acting on any module M, to say that M is dualizable over B is to say that M is projective as a B module. No, finite, compact, finitely generated projective. Actually, that's the same fact I used here. It's just that the field is semi-simple, so projective is vacuous, and finitely generated means just finite dimensional. So I'm just using the same fact here, and because this algebra B can be non-semi-simple a priori, then we have to be careful, and we need to require that M is projective. Okay. But so in other words, we look at this algebra A, we look at it as a module over its double, so to speak, and we ask that this is projective. So this being projective, that's the definition of what's called separable. So an algebra A is called separable if it's projective when regarded as a bimodule, and over C, this is equivalent to A being semi-simple, i.e. A just must be a direct sum of matrix algebras over C. So you start to see something. We keep running into semi-simple things when we're talking about these defects and fully extended stories, and what's going to consistently happen is that getting up to the very last level is going to be some, what I feel to be reasonable requirements, and then getting fully dualizable, getting the very last bit, is going to really force you to be much smaller. And you can also think about, in terms of Constantine's lecture, at least the principle of fully dualizable theory, you should imagine that there's some kind of path integral formulation that's going to involve summing over spaces of morphisms, and the finiteness and the semi-simplicity is going to imply that all the sums are manageable. There's nothing tricky.
Okay. I'm still confused about this thing that you said about the left adjoint of the evaluation relating to the co-evaluation.
Let's discuss that after, yeah.
Okay.
Sorry. There is a statement like the one that he asked about. I'm not even sure if I got it right off the cuff, but we'll discuss it after. It's important, but yeah. Okay. Great. Right. Okay, so what we've concluded is that you're two dualizable if and only if you're finite dimensional and semi-simple. Let me state as an exercise the parallel situation for k-linear categories, since that's somehow also important. So C okay, so there's k-linear categories. For experts, there's something called presentable categories. I certainly will not tell you a definition of presentable categories, but I'll give you the exercise anyways. So here, these are small categories. When I talk about categories, it means that the objects form a set. A small category is always one dualizable. And the one dualizable, the dual is just the opposite category instead of the opposite algebra. So the contravariant category. And a presentable category is dualizable if, I'm not actually sure about if and only if, C is the co-completion, the free completion of a small category, the appreciative category. Okay, and then in both cases, it's two dualizable if and only if it's a finite semicircle. Okay. Great. All right. So now I can, with this example in hand, I want to return to an additional bit of structure in the Cobordism hypothesis that we didn't touch on before, that we could have. So orientations. Okay. So now we're going to see the real power of homotopy theory for these kinds of problems. Right. So the n-dimensional frame TFTs, these are some functors from this framed Cobordism category to S. And we've said that this is equivalent to the fully dualizable objects. Now here's a very beautiful observation, which I think was Jacob's. I don't know if it was in Barnes Dolan. This category has an action of the group SON. Remember that a framed cobordism means that the tangent bundle has been trivialized everywhere, and you can always just change it globally. You can globally just change the framing, so you get an action not of like, you know, SON bundles or something exotic, just SON. It acts there. And this is a homotopy equivalence, so that means that that SON also acts here. But there's a subtlety, which is that we're doing homotopy theory. So the notion of an SON action is slightly more subtle than you might first expect, which is that, so this action, which gets equated to this action, is the data of a map from BSON, so point mod SON in the homotopy sense, to B aught of S. So S has, so I can talk about automorphisms of objects of S, and I can require that everything is invertible, that I only consider invertible gadgets, and then that's a group, and then I can take its classifying space, and the data that I need to give is a map like this. That's the data of the action in homotopy terms. So that's something you get canonically. And then the theorem, so the corollary of the Cobordism hypothesis, is that that oriented TFTs with the same target S. So these are, first of all, by definition, this is framed ones. And then we take the fixed points. And then this is equivalent to, of course, S. Fully dualizable, and we take the fixed points. Okay. All I'm saying is that, heuristically, a framed TFT involves this extra choice of a framing. An oriented TFT says I want to forget that framing. So the way I forget that framing is I quotient by SON. It's a little bit more subtle than that because, for instance, not every n-manifold can even be framed. The genus 2 surface does not admit a 2 framing. But the beauty is that this homotopy theory sort of deals with that. You do it locally. Every manifold can be locally framed. And then the homotopy fixed point structure gives you exactly what you need to patch a local framing together and then to not worry about the ill-definedness. So now, okay, to make sense of this, I need to tell you what a homotopy fixed point is. And it's a nice definition. So, so this upper thing means homotopy fixed points, and the definition is homotopy fixed point of the action functor. The homotopy fixed point is a null homotopy so I take this map of spaces and I give you a contraction of that map down to a point. I have to give you that data. So first of all, it has to. There's a condition that such a data has to exist, and there's a structure which is I have to tell you how to do it. All right. So I wanted to do this aside right now because this is the one place where you can convincingly actually work this out, is in a two-dimensional case. So okay, here's some facts. So let's let n equals 2. Okay, so SO2, that's just the same as the circle S1 as a topological group. And so BSO2 that's just BS1, that's CP infinity. This is a classic fact from topology. Forgive me if it's not familiar. Sorry, not C infinity, usually CP infinity. And now, here's something that's really special about SO2 that you won't find anywhere else, which is that this has a really lovely iterative structure. So you can write this as a CW complex. It has a single 0 cell and a single 2 cell attached to it. This is CP1. And then you attach to that a single 4 cell. This is CP2. And you keep going, always attaching cells. And so first of all, there's only one cell in each dimension, and in fact, only in each even dimension. I'm going to use that now. So the application of this fact is that to give a map from BSO2 to any other space X is not actually such a crazy thing to do. I have to tell you where E0 goes. So in our case, E0 is going to go to some automorphism of the identity functor. So it's going to go to some automorphism gamma of the identity functor of some object X that we've anchored our TFT on. Well, to first approximation, that's all that I need to do. And then E2. No, sorry, I said that wrong. I'm sorry. I said that wrong. E0 is just going to go. These are connected spaces. That has a single 0 cell. This is a single 0 cell. So this first one is just trivial. E0 is just going to go to the point there. If you like, this is X. This is the X that we're anchoring to. And then E2 is going to go to some kind of automorphism gamma of the identity of X. I said the identity of the identity because it's not a, if it was a 1 cell, it would go to an automorphism of the identity of X. It's a two cell, so it goes to an automorphism of the identity of the identity.
Just to clarify, is X an object of S?
Yeah, right, thank you. So you see, to give the data of the fixed point, so to give the frame structure, I've kind of already said where my object goes, and now I'm trying to ask whether I can, elevate that framed TFT to an oriented TFT, and so so this has a unique point. This has essentially also a unique point. But if you like, I can think of that point being based anywhere I like in S, and I've just chosen it to be X. Yeah, does that make sense?
So just to reconfirm, so big X is the connected component of S that contains small x. Am I wrong?
Shoot, sorry. This is, sorry, I see the confusion. Yes, I'm sorry, gosh.
I mean, this action map doesn't.
I was just explaining you in general, if you want to map BSO2 to any space Y, that there's this procedure. And I apologize. Here, I really apologize. Here, now I mean X to be the object in the other category. I didn't mean to use the same letter twice. Sorry for the confusion.
Sorry, I'm still a bit confused. I mean, the map act doesn't involve the object X at all, right? The map act is just.
It doesn't. That's true. It doesn't. That's right.
So the place where X comes in is when you now define the null homotopy of. So there's the constant map, which map picks out X or something, and then you want the null homotopy.
Okay, let me answer your question. So yes, the notion of an action doesn't depend on S, but this is the space of fully realizable objects, and so yeah. What I mean to say. Yeah, I think you said it right, that I pick out a particular connected component, and moreover, I am imagining picking out a specific point in that connected component, and I'm anchoring this there. Is it sounding not right?
Still a bit confused.
Can I maybe just, maybe I'll go into an example, and that might actually clarify. It's possible that I said something wrong, but we'll see how it looks in the example. Okay. Right. So in our example, right. So in our example, okay, here's the beautiful thing. If the target S. So in our case, our target S is a 2 category. And in particular, as being a 2 category, this implies that, all the higher homotopy groups, I greater than or equal to 3, are all 0. It's what's called a truncated, if we think of this as a space, it's truncated. It only can have interesting stuff happening in low dimensions. And so the first remarkable thing is that the data of a map from CP infinity into a 2 type, it simply is completely oblivious to all this extra stuff. Once I tell you how to extend, once I tell you what to do with these 2 cells, I can extend it, and there's a unique such extension. So actually, and we've agreed that this is sort of not so important. So there's just this this bit of data.
David,
Yeah.
does it mean maybe that you need here gamma to be automorphisms of the identity and not of the identity? Because that would be a free morphism, right? Or am I wrong?
Yeah. There's good corrections. Let me do the example, and then let's correct it. Yeah. So it's always good to engage the audience with some confusion. Okay. So first of all, the action of BSO2, I'm claiming, is just given by where we send this 2 cell. And I'm going to give you a formula for what the action is. I think we'll probably see that Jordanis is right. So what the action is going to do is for every A, so uniformly for every A, I'm going to look at its identity in an identity bimodule, which is A as an AA bimodule. And I'm going to map that to a bimodule, which is this. So I'm going to take the vector space A. The vector space A, it being finite dimensional, is isomorphic to its double dual. Let me put the double dual here to clarify. So the vector space A is isomorphic to its double dual as a vector space. But a priori, that isomorphism, even though it's natural, it needn't commute with the action of A. So there's a new bimodule that I can get where I twist the action of A by using the natural isomorphism of vector spaces from A to A double dual. This is the image, so E2 maps to this gadget. So I think this will start to help correct what I said earlier. Okay. And what is the data of a homotopy fixed point? I want to identify this thing with just the trivial action, which is where I didn't do anything. So in other words, what I want is a natural isomorphism from A regarded as an AA bimodule to A regarded as a bimodule with the right action twisted. And now the point is that this is the same thing as a symmetric, additional structure of symmetric Frobenius algebra. Okay, and then a symmetric Frobenius algebra structure itself has a nice interpretation in terms of these pictures. So if we have this TFT attached to A, then what we attach to the circle is what's called the zeroth Hochschild homology of A, or the trace of A.
Shouldn't there be a single dual on the A if I want this to be true?
No, I think you're remembering another formulation of a symmetric Frobenius algebra would have me put like two different duals here, but no,
As a related question, can you maybe explain where the double dual comes from?
why is the double dual appearing in this formula? I wasn't planning to explain that, to be honest, but basically there's a nice calculus for these computations that was developed by Christian Reprise. Like everything, it was in this example explained by Lurie. So this E2, it has a sort of topological interpretation where somehow the algebra A with its AA bimodule structure is, you think of as attached to an interval framed. And then this E2 is attached to this picture, which is like a loop-de-loop. Okay. And then what you can do, okay, this bit is just a symmetric structure, and then here you're using the duals, various duals, and you can really use the duals as vector spaces. So you've twisted, when you do around this loop-de-loop, you just compute and you see that if A enters this thing on the right, say, then by the time it winds its way back around, it's been twisted by the double dual automorphism. So that's helpful, that's the intuition. Okay, so going back, if we believe this theorem, I want us to sort of believe this theorem for a minute, that the data of this trivialization is the same as the data of a symmetric monoidal structure on A, and then I want to just convince you that you could see it more directly. So the value on the circle going really slow, but I feel like the questions are good, so I'll just keep going slow. Maybe I'll summarize. I'll have to summarize things a bit more in the second half. And if I bat away a question, it's not because it's bad, it's just like, if I answer every question, we'll just run out of time. So let's think about Z of the circle for a minute. So as before, we should really think about Z of this thing if we're being careful about framings. And what is this? Well, this is just Z of this tensor over Z of this with Z of this. Remembering where we're working in the Morita category. So this is A. This is A tensor A op. And this is A. So this is A tensor with itself over A tensor A op. This is the same as the linear quotient of A by its commutators. And this is what I was calling HH0. I.e., this is the thing which is the universal source for traces, for traces. Mapping out of this is the same as giving a trace on A. Okay, but what is a Frobenius structure? A Frobenius structure is exactly the data of a trace from A to the ground field. And so that is what we get when we take the circle and we cap it off. So this is the Frobenius trace. Okay. Z of this determines the trace. The trace should be non-degenerate. You work that out from one of these topological diagrams, and it should be symmetric. You also work that out. Good. So what we did is we unpacked this fancy notion of homotopy fixed points. We saw that it predicts, well, it doesn't predict, it proves that you have a symmetric Frobenius structure on A, and then we reinterpreted those as obvious structures that we get just from topology of surfaces. So let's see. Jordanis, do you want to help me fix this, or should we?
Well, I don't know. I thought that one cells would map into automorphisms of X, and then the one level higher would be automorphisms of the identity of X.
Yeah, very good. Okay, thank you. I got carried away with my identity of identities. And then the other thing to say that was noted before is that the action of SO2, it's not per point, it should be natural in all points. So that is to say that E2 goes to the automorphism of the identity functor of X, but it's natural in X. So it's an automorphism of the, yeah, in that sense. So this formula holds not just per A, but it holds for all A in a natural way. But then when we go to trivialize it, we're fixing an A and trivializing that. Great, thank you for the corrections. Oh gosh, is it lunchtime? Oh. Okay. All right, so what time am I meant to stop with this?
I don't know, 5 minutes, something like that.
That's okay. This it's worth doing this example slowly because everything else that follows will be built on this. Let me just say an example that is of relevance here. So we can take A to be the group algebra of some finite group. And that has a Frobenius structure where the trace of G is just delta GH. Which is to say it's either 1 or 0, depending on the identity, depending on whether G is the identity or not. And there's a lovely formula that you can work out, and in fact you can work it out in different ways. and you get lots of nice combinatorial identities. So, right, I've told you now we've got a fully dualizable, we've got a TFT, it's on an oriented, it's an oriented two-dimensional TFT. The question should be, what does it do on surfaces? And it's very nice. So it's the sum of what are called principal bundles with group G. So this is just my notation for a principal G bundle. Here G is finite, so if you like, it's just a topological cover of sigma with fundamental group G. And I'll write this in two ways. We take 1 over the automorphism group of the principal bundle, or we could write this as 1 over G. So this was over isomorphism classes, or we can rewrite this as the sum of 1 over G times just the sum where I don't mean isomorphism classes. For instance, I choose a framing times 1. So either way you bake it, this is the number of principal G bundles. Counted in the suitably stacky sense. I won't give it now, but if you know the character, so if you know, an application that's very nice. If you know the characters chi, the characters of all irreps of G, you get a formula. I think it's something like ZG sigma G is the sum over all the irreducible representations of chi raised in fact, it's just the dimension of G. So forget that I said characters. There's another formula involving characters. Just the dimension of the irreducible raised to the G minus 2, if I haven't messed that up. So don't I might have got this wrong. But the point is that now because of all this TFT stuff, you get a uniform formula in G, which is very lovely. Okay. I think what I'll do, somewhat strangely, is I'll just state where the third peak is that we're going to go to next, just so you can have it in your mind while you eat your lunch. But then I won't really do much more. But of course, if you have any questions about the 2D case, please let me know. So 3, now we're going to work with, so before we worked with a 2 category of algebras, now we're going to work with a 3 category of tensor categories. Okay, and this is how we'll start to treat the kinds of examples that came up in Xiao's lectures and in Kayla's lectures. Okay. So I think what I'll do is, before I tell you what the 3 category of tensor categories is, before we break for lunch, I just want to give you you know a definition of tensor categories. I want to give you a different one. And so instead of telling you that we have a category with a tensor product functor and an associator and a pentagon axiom like in Kayla's lecture, I'm going to not do that. And instead, I'm going to get on my homotopy wave boat. So instead, there's a topological category, which is the category of disks, framed disks. So this is a category, it has objects which are just disjoint unions of R. Finite disjoint unions of the topological space R. And then it has HOMs equals the embeddings of such. But now I'm going to write the space of embeddings. And by saying the space of embeddings, I don't have to say any more, but I can. So because everything I'll say now is tied up in that word space, the two HOMs are going to be isotopies between embeddings. The three HOMs are isotopies of isotopies.
Do you mean framed embeddings?
Framed embeddings, thank you. Thank you. And so on. So we're just going to look at isotopies of isotopies. Okay, and so now a different definition, a tensor category. This is a functor from disk 1 framed to the category of categories. That's my definition of a tensor category. Why do I say this is the homotopy way? Because what I've just said is that now that data is the same as saying that if I give you an interval, so first of all, an interval is going to map to some category, call it C. But what I've also told you is that if I embed a bunch of little disks inside of a big disk, that I have to give you a functor from C, tensor C to C. Because this picture denotes an embedding that has to go to a functor, and it goes like that. Now, the kind of thing that you worry about when you write down associators is, well, wait a minute, what if I first go C tensor C by multiplication tensor the identity, and then I instead go identity tensor M to C tensor C, and then I multiply. You say, wait a minute, I need to give you an isomorphism like this, and then I need to go and work, this would be the associator, and I need to go check that it satisfies some axioms. But if I just say it this way, that it's a functor, then all that data is automatic. Because these things are isomorphic, so if I take this picture and I just choose an isotopy, which I can choose, that just happens to bring these two guys really close together and this one far apart, and then I just choose to regard that as factoring through, that's this one. Or rather, that's this one. I've multiplied those two first. And then once I've done that, then I can again make a choice to bring them all three together. And that's the multiplication. Yeah? So in this way, I'll automatically get an associator here, which is just tracing through this path in the space of isotopies. And then the fact that it satisfies the pentagon axiom is a tautology. It's just that this space, once I've stapled these four things onto the page, the space of possible things I can do is just contractible. I can never hopscotch this one past. All it can do is kind of move around here. All this one can do is move around here. And so the space is contractible. So any diagram that I would write down is well defined. And this is especially useful if you, for instance, care about infinity categories or DG categories or something. You would not want to have to keep going with, Michaela mentioned the pentagonator, that is a thing, and then the pentagonator needs to satisfy another thing, another thing. It's just, you don't do that. Instead, you just say what you want to do, and then you unpack those things Okay, so I'll stop there. Thank you.
I mean, maybe this was implicit in what you said, but this is unique to some. This is not just a functor, right? It needs to be like monoidal or something. It needs to be compatible with.
Yeah, sorry.
Percentage joint union.
Yes, I apologize.
To tend to product.
This is a symmetric monoidal function, but that's it. Yeah, where the disjoint union of disks maps to the tensor product of categories. Absolutely.
If there are no more questions, let's thank David again.
Okay, welcome back. So, I want to talk now about the target higher categories that we will use to understand all these calculus of defects and so on, and how we relate them. Let me just, before I start talking about the higher categories of algebras, let me just go through the three main examples of algebras in dimensions 1, 2, and 3 that I want you to have in mind. So I spoke last time about the calculus of algebras. You have just a category of little disks and their embeddings, and you treat everything up to isotopy, and then this gives you back, if you really insist, you can read off from this kind of combinatorial data. We're going to talk about the HOMs in a minute, but we've already seen something like this with the notion of bimodule. And so there's another category of disks. So this is really about a category of disks where I can have two colors of disk. One I'll just formally call A, and the other I'll call B. And then I have another color of formally a disk with a defect. Again, the HOMs between A and B now are just the functors from the category that I've cartoonishly depicted here into the same target space, so the same category of categories. So that means I have to attach this disk colored A to something that's an algebra, just as above. This disk called B goes to an algebra, and now this one is different because I don't have, what I don't have is a, the disk labeled M. If I put two of them next to each other, I can't embed these something with two marked points into this thing with one marked point in a way that respects the marking. So this M no longer has an algebra structure, but I can take A on the left and B on the right, and I can embed the disjoint union of that little disk, and that little disk inside this bigger disk. And notice that this bigger disk is just another copy of the little disk. So this tells me that I do have A tensor M tensor B mapping to M, even though M doesn't have a monoidal structure. Okay, so that's, in a minute I'll say how we're going to combine those into a category. But I want to give you some more examples. So now I'm just going to increase the dimensionality. So two disks. Now I'm just including little two-dimensional disks inside one another. Again, if I just record where the little disk called R2 goes to, that's some object in my two category of categories. That's some category. Again, I have now not just a multiplication, for any sort of configuration of points, like any way that I want. So there's three things, and there's no ordering, they're just living in space. I have a well-defined way to multiply those in to get something in A. And then those different multiplications are all isomorphic as soon as I start isotoping these things around. So for instance, I can get something that starts to look like a braiding if I just swap those two pieces around. So the category disk2 framed has all the structure that you might want encoded in it. And now, if I wanted to list things out explicitly, what I would need to do is sort of break this symmetry that I've made and choose an axis that I want to prefer. And then I can always insist that I'm only going to consider disks that sort of live on this axis. And that will give me the associativity, the multiplication, sorry, the category, the multiplication, the associativity, and the pentagon axiom. And then I can remember that, oh, actually, there's nothing bounding me to have done that. I get the grading, and it will satisfy the hexagon axiom. Okay. Right. So the plot thickens a bit when we think about bimodules. So codimension 1 defects have a nice story. So again, we're going to consider manifolds that are sort of cleaved into two parts. A is going to be what controls the behavior over here. B is going to control the behavior over here. And along this defect, we have a new thing. And I'm just going to name that C. So C is the image in categories of this kind of disk. And now you notice something nice. C itself is composable. So I do have a map from C, tensor C, back to C, which is actually just this picture, but in yellow. But there's more, because so there's more data here. So let me just draw this picture again. So if I have an A disk, I can take this A disk and I can include it inside this C disk. So that gives me a functor from A to C. I have a similar functor from B to C. I can combine those together to get a functor from A tensor B to C. So far, so good. But now this functor is monoidal if I choose, for instance, to stack. So if I stack my disks this way, then of course, if I include here and here, that's the same as if I had multiplied here and then included here. And I don't have to go and check anything. That is just a tautology, what I just said. So what that tells me is that this thing, if I equip it with its monoidal structure, this thing with its monoidal structure, this is a monoidal functor. But then something else that happens is that it's not just a monoidal functor. If I take something out here, and I take something here, then this one is free to move about in space. So I could say that I'm going to tensor them in this order, or I could say that I'm going to tensor them in this order, and I get manifestly the exact same answer. I'm just including things I'm just including open sets, and they get like identically the same map. But when I interpret that in terms of this, what it tells me is that if I put an object here, call it X, and an object here, call it Y, I have a half braiding but it only lets me half braid the things that came from outside. So that tells me that, so if you remember, there's this notion of the Drinfeld center. And that tells me I have a canonical lift from this multiplication structure to the Drinfeld center mapping down here. Okay. So this whole data is what's called a central algebra. that it's a nice structure. Oftentimes when I'm talking to people, they get confused about the role of the Drinfeld center. Maybe I won't go into it. I think that there's sometimes confusion about the role of the Drinfeld center. Okay, and then let me just say, so those are the HOMs. I won't go out in as much detail, but the two HOMs now are just defects where we do one more. So we put A, B, we choose two different central categories, C and D here, and then we put a bimodule in the middle. We just unpack what the coherences are. Okay. So in both of those cases, in disk 1 and disk 2, there's only one thing we need to do, which is, so here we got two category. So we had, we had a one category. So we had the objects were the algebras, and the one morphisms were the bimodules. Okay, but everything I said didn't depend on what S was, what our target was. And remember, we had this target, which was just some kind of categories. And so there's a sort of additivity thing that happens. Now, this is a two category, so I'm going to be able to add two more structures here, which are just about morphisms here. So there's two morphisms, are functors, and three morphisms are natural isomorphisms. Natural transformations, let's say. And this thing, this is the definition of the three category tense. The three category of tensor categories. This is the home for, so this is the home for Triaviro. In sort of more traditional classical topology, Triaviro theories, and more in the framework of what we've been doing this week. This is where symmetries of 2D TFT, 2D QFTs live. So if I have a 2D TQFT, then I thought, so in the way that you usually hear this from physicists, a 2D TQFT has one-dimensional operators that are codimension 1 operators. So in the physics terminology, there's this thing where you're supposed to talk about codimension 1, and yet in the Friedmore Telemann, there's a different picture where you're supposed to put it at the boundary of something which is codimension -1, so one dimension higher. And the point is that this little bit here is what lets you jump up. It's because you're working in categories. Okay, I just want to draw one more picture. So disk 3, just to make sure we're all on the same page. I certainly won't. So disk 3. Sorry. I need to do Burr tense. This will be important. So Burr tense. So this has objects. Braided tensor categories. And remember, a braided tensor category is just a two-disk algebra. One morphisms are central tensor categories. Two morphisms are bimodules. Three morphisms are functors. And four morphisms are natural transformations. And I won't write it all out, but I will draw you a picture. I'm also going to want to talk about symtense. And this is, objects are symmetric tensor categories. And then that's line, and this is a 5 category. So this 5 category will feature maybe on Friday's lectures. And the picture you should have in mind, of course, is now we draw pictures in 3D. So we got 3-dimensional balls. And they're moving around up here. Then we've got a braided tensor category, and then we've got line operators, and we've got point operators, and the whole thing. Okay, so this whole rich. I'd like to share a funny story. I'll explain a result later about invertibility in braided tensor categories that we submitted to a journal. I got a positive review, and the person said, I suspect it might have been one of my current collaborators who was not my collaborator then. Got a positive review. It said they've solved this invertibility question, and lest the editors be worried that this is just one in a parade of tedious results climbing up the category level. Rest assured, there's nothing interesting to say about the symmetric tensor category of 5 categories, and they were wrong. So I'll talk about that a bit. I think it's still worthwhile to study that. Okay.
David?
Yeah.
So is the rough picture that you drew here that n stratified EN algebras make up an n+1 category, or?
That's right. EN algebras form. So the EN algebras. So yeah, So what's the numerology? Thank you. So if you look at EN algebras, so let me just say disk n instead. Disk n and EN are the same. So if we look at disk n framed algebras in some S, and this is a K category, then the collection of these things is a n plus K category. And I should be giving some more attributions here. I've presented as if it's obvious, but this was not obvious at all. This was a construction of Johnson-Fried and Scheinbauer, and independently in a different model, Huxing. So I've been, making this point that you need to be careful about even giving definitions of higher categories. Here I just sort of blithely told you what the morphisms are. The compositions are what you would expect, and what Michaela has already sort of referred to. For instance, if I would have A, as one example, if I would have A with a central algebra to B and another central algebra to C, what I would do is I would tensor over B. So I would take about this, what I would want to think about this is, as we're probably all expecting now, that these guys are just really, really close. Yeah? Okay.
I'm sorry. Is this the collection of these algebras is a category, or
Yeah, sorry, the collection of disk n algebras in a K category forms an n plus K category. So for instance, a disk 1 algebra in the 2 category of categories is a tensor category, and they form a 3 category because 2 plus 1 equals 3.
Are the morphisms like natural transformations between the functors? Or?
Yeah, exactly. So exactly. Thank you. So there's sort of the bottom level is just pure topology manipulations, and the next level are just algebra manipulations. That's the dichotomy I wanted to emphasize here. Yeah. Okay. Great. So now what I want to do is start to go through that dualizability mountain again. So if you remember, we were on dimension 3, and now I can talk about dualizability in tensor categories. So here it is. 1. So every tensor category is one dualizable. And of course it is, because we know what its dual is. It will be the opposite monoidal structure, the opposite tensor category, and you'll have the same bimodule. It's the same story. So that's due to Lurie. But I'm going to go ahead now and also mention Gwilliam-Scheinbauer. So Lurie definitely knew this and wrote a proof of it. But you notice that that in the proof it was very general. It just was about topology really, and Gwilliam and Scheinbauer made that precise. So in fact, every disk in algebra is n-dualizable. We'll come back to that. So what I'm saying is there's some amount of dualizability that you just get from topological manipulations, and it's not to be surprised at. Okay, 2. So every CP rigid tensor category is 2 dualizable. So this we proved with Adrian Brochet and Noah Snyder. This is a bit anachronistic because the result to follow came first. I'll discuss. And then what you really want to know is about 3 dualizable. So by the way, I don't think I ever explicitly said it. We talked about fully dualizable, meaning that you could climb your way up with all these adjoints. And if you only get part of the way there, then you're called 2 dualizable. Or you're called K dualizable if you can only get part of the way up. So for instance here, what the statement is that there's a 3 category. So in the first one, there's a 3 category of tensor categories. So I could try, given that it's a 3 category, to construct a 3-dimensional TFT that's supposed to spit out numbers. But if it's only 1 dualizable, then I realize all I can do is define a 1-dimensional TFT that spits out categories. It's still interesting to be able to do that. Here I'm saying that if I have a CP rigid tensor category, all I know for certain is that I can construct invariants of surfaces, dimension 2, and they won't be numbers, but they'll be vector spaces. And then the full dualizability result is that every fusion category is 3 dualizable. And this is Douglas, Snyder, Douglas, Schomer, Kreis. That's one person, Schomer, Kreis, and Snyder. Yes.
One question. When you say 2 dualizable, you mean that the evaluation and co-evaluations both admit both adjoints?
Yes.
But also that the adjoints admit adjoints?
I think if the...
That's automatic.
So let's see. So 1 dualizable is just that you have evaluation and co-evaluation. 2 dualizable is that the evaluation and co-evaluation have adjoints. And then 3 dualizable is that those have adjoints, that the unit and co-unit have adjoints. Yeah, thank you. So there's an iterative process and you're just climbing up a ladder, and if you get high enough, you say you're K dualizable. Okay, good question. So every fusion category is 3 dualizable. That was a result of Douglas, Schomer, Kreis, and Snyder. If you put some mild assumptions, this is almost an if and only if at the bottom here, although it wasn't obvious from their original construction. So this was an important result, I think. This paper was, I think, published in the Memoirs of the AMS, and it really, so what this does for you is it constructs Turaya Viro as a fully extended TQFT. Before, what people did was they did the opposite. So notice there's something we're doing. So we're starting at high codimension, where we have a lot of structure, and then we're trying to build up the top dimension using finiteness. Whereas what is more traditionally done is to start at the top dimension, where things are concrete, where you just have some numerical invariant, and then you try to build down by guesswork. So you just try to guess what structure down here you could have used to compute that, and you try to build down. So it's kind of funny, these two things go like this, yes. Okay. So I should say what CP rigid is just very briefly, but it's not so crucial. Okay, so a presentable category is one where every object X in C, presentable category C, is one where every object X can be written as the colimit over all the projectives mapping to it of Hams P, comma X, tensor P. Okay. This might look a little bit technical. Projectives are like the nice objects that you want to work with in category theory. To say that something is presentable is to say that that you can write X as in the basis of the nice ones. So he really invites you to think about a Hilbert space. Analogy.
So shouldn't this just be a colimit over P? Or isn't the indexing of the colimit already?
Yeah, sorry, colimit over P, yes, thank you.
Or the other way around, colimit over the map.
Yeah, colimit over P, yeah. It's really a co-end, so it's, but let's not worry about it. It's a certain colimit that has, whose terms are this, but has more structure than I'm willing to write on the board. I'm happy to explain what coends are to anyone afterwards. But the point that I want to make is that if you have H, a Hilbert space, so for instance, say that H is L2 functions on S1, as an example. So the nice thing about L2 functions on H1 is that there's a basis of functions called e to the I n theta, and you like those for some reason, they're nice. Sorry, 2 pi I. Anyways. But this is not really a basis, right? This is not a basis for that vector space. What's true is that any function in S1 can be written as an infinite sum of some so that's for analysis, and so you want, this is a sort of categorical version of that. You have some nice functions that you like, that's the projectives in this analogy, and you want to be able to say that everything is a possibly infinite limit, and that's what's happening here. That's the notion of presentable. And then if C is presentable and tensor, then you say that C is CP rigid if for instance all projectives have duals. So remember, dual just means like literally that you have evaluation, co-evaluation. So when we work with finite categories, we always you ask somebody what a rigid tensor category is. You just say that every object has duals, and that's fine. But if we want to talk about things like infinite groups, for instance, then that's a bad idea. Because, or for instance, if we want to do algebraic geometry. So suppose that now that I'm running out of letters. W is some algebraic variety. And suppose that a perfectly good example of a CP rigid, even presentable tensor category, would be to take quasi-coherent sheaves on some algebraic variety. Let's even say it's smooth. So variety is like a manifold, but where everything is polynomials. So now you look at the category of coherent sheaves or quasi-coherent sheaves on W. This has its projectives. And if you've been wondering what this word projectives means and why these are special, then this example will motivate it. The projective, these are the vector bundles.
Shouldn't there be some finiteness assumptions or some compactness assumptions on the projectives? Or do you really want every projective to have duals, or only like the compact projective?
Well, compact projectives, thank you.
Similarly, on the left, do you also want this colimit to be not...
Thank you. Thank you, thank you, thank you, thank you. Over P, well, I never actually said, so that's okay. But compact projectives, yeah. Thank you very much, yeah.
This is a bit stronger than presentable, right? What you write here.
This is, yes, this is, yes, this is, yes, sorry. This is,
compactly generated.
yeah, that's right. Nice. If for every object in C, sorry, yes, of course, you're right. And then C, a nice tensor category. Thank you. Yeah. There's a technical word, it's a pre-sheaf category. Okay. Yeah, thanks for all the corrections, that's important. Right, so the point is that the compact projectives in algebraic geometry are the vector bundles. And the vector bundle sitting over W. And then they have a dual, which is just to take the dual vector bundle. And that will exhibit them as rigid objects, as having evaluations and co-evaluations. But on the other hand, if you took something like a skyscraper sheaf, which is a perfectly nice thing to do in algebraic geometry, a sheaf that's sort of just supported at one point, that certainly won't have a dual. Can't possibly have a dual. So there's a lesson here, which is just that if you want to get beyond these little finite examples that people like to think about, and you want to do something with continuity, with continuous symmetries, you need to learn some algebraic geometry, and you need to learn a little bit of category theory, but not too much. This was all sort of stuff that people did in what's called the Australian category theory school in like the 70s or 80s or something. But if you're a physicist, I invite you to think that I'm just doing some abstract version of functional analysis. Maybe, let me just, allow myself to take that slightly further. I'm suggesting that we think about categories as Hilbert spaces. I also like to think that the Hom functor to the category of vector spaces, this is like the inner pairing that you have on a Hilbert space. All right, you can take the inner pairing of the inner product of two vectors, and you get a number. Likewise, you can take the Hom pairing between two objects in a category, and you get not a number, but you get a vector space. But you think of that as a categorification. And the lovely thing about categories is you get worried and you have to invent analysis if you get infinite numbers. but nobody minds if you get an infinite dimensional vector space. So it's like you can do analysis without worrying about that kind of thing. Adjoints, adjoint functors are just like the adjunctions of maps, and you can play this stuff all day. And the reason I kept pestering Hoshan is that with this analogy, the notion of unitarity, I think, I wonder a bit about the notion of unitarity, because if we're thinking about the category as being the stand-in of the Hilbert space, then the unitarity seems like it should be something functorial about the category and not about the Hom spaces per se. Argue about the Hom spaces would be asking for good properties of this inner product, and I think you've already nailed that down. Okay. So, to summarize, it's just to say that there was some beautiful algebra done in this paper about fusion categories, and we were motivated to understand how to move beyond the finite world to the infinite or continuous world. We just needed to learn some category theory, and we did, and then we were able to generalize their result. Of course, we don't get top dimension, because the top dimension is going to be like summing over all the objects, and we just went to all this trouble to allow infinitely many objects, so we're not going to get numbers. So we're not going to expect full dualizability. Okay. So let me explain a bit of how this proof goes. In the DSPS one, and this one is similar. So I would like hereby at this conference to coin the term the babushka principle. So does everybody know what a babushka doll is? So a babushka doll looks like this. Should have practiced this beforehand, so it kind of comes up like this, around like this, like that. It's got a little crease in the middle, and then you can stack them one inside another. I thought about calling this the turtles all the way down principle, but this is only one word. So you have algebras in algebras in algebras, and only at the very top do you change what you mean by algebras to say idempotents. So what I mean is that the proof that we already did in great detail for dualizability of algebras, we're just going to repeat that proof in an ever-growing cascade of contexts, and it's going to keep serving us well. So we're just going to keep nesting the same proof. So here's what I mean by that. So let me do two. Let me prove the second one. Okay, so what do I need to do? I need to pick up a tensor category A, and I need to tell you its dual, but we already know what its dual is. It's the opposite category. So that means it's the same. So I need to be clear now. Let me start writing tensor up. So A is a category. So I could have meant the contravariant category, where I reverse the Hom spaces. I don't mean that. I mean it's the same category, but where I do the opposite tensor product. I just tensor things in the opposite order. That's the dual. And then the evaluation and the co-evaluation, just like in the case of algebras. Sorry, let me use the letter C. I'm trying to be consistent with my letterings. Apologies. So the evaluation, the co-evaluation, remember these were just C as like a C tensor C op vect bimodule, just like before. Okay. And then the key thing that we needed to know was that C tensor up dot C mapping to C. So this is a bimodule. This is an algebra. It acts on itself as a bimodule. It acts on this as a bimodule. And what we needed to know was that this had a nice, well-behaved splitting. That was, remember, the notion of separable for an algebra was that you could split this thing. But here's something really nice, and it goes back to this analogy with Hilbert spaces. I have this multiplication. Unlike in the case of algebras, I have nothing left to do because this thing already has a right adjoint. I'm working in a setup where every functor has a right adjoint. That's the point, just like in Hilbert spaces. If I have a nice map between Hilbert spaces, it automatically has a right adjoint, as long as it respects the inner product. And T is a functor, so it respects the inner product. But the only issue is, does TR, is TR also well behaved? So it exists, so T was nice, the right adjoint exists, and I want to know whether the right adjoint is well behaved enough. And the answer is yes, and I'll say exactly what I mean. So in fact, TR is so well behaved, so this is called monadic reconstruction. What it says is that the C, the category C that we're trying to build, we're trying to study, is actually equivalent to TRT 1C plus C. Explain what this funny, sounds like I'm just stuttering, but I'm not. Modules in C. Okay, so what I do is I take the unit in here and push it into here, it just becomes the unit, and then I pull it back. Because of CP, so CP rigidity implies that this thing here is an algebra. And it implies that C is equivalent to modules for that algebra. Okay? But that's us. We're done. Because we already showed that, A mod is dualizable. And when we did the two-dimensional thing, the whole point was that we knew that A mod was one dualizable. Here we're asking whether this adjunction is dualizable, and we've just reduced it to the previous case. So that's what I mean by the Babushka principle. We just repeated the same proof that we had before. We had to do the same check. And then miraculously, using rigidity, we reduced that check to the thing we already checked. So it's very satisfying. Okay.
So, principle breaks down. So you said for disk N, you have up to N dualizability, and then this principle will break down to need more dualizability than that.
No, disk N is always N dualizable.
Yes.
And then you start climbing up, and you start to run into doing more and more algebra with categories. But category theory tells you how to climb this ladder, and it gives you a recursive way to climb that. And you get more and more requirements. So for instance, I said out loud, but I didn't explain precisely, I needed CP rigidity for this construction to work. The fact that C is actually equivalent, it wasn't automatic. I needed this extra property. I had to go in and look it up in some category theory textbook, but they just tell you exactly what you need, and that's your definition. So by the way, CP rigidity, like representations of any group, whether finite or infinite, any algebraic group, any finite dimensional representations of a Lie group, all of these things have this property. So you can access large constructions. Okay. Great. Okay, I want to state some results for braided tensor categories now.
Can I ask you a quick question?
You can, certainly.
What about going in the other direction? Do we need to, so we have like TR following T. Do we need to show that T following TR is nice? Or is
Yeah, you need to check some other things, but I don't know, check everything. Yeah. This is the idea. Well, actually, no. Sorry. It's a reasonable question. Remember, the other thing was just in the associative algebras. It was just that we needed this thing to be a finite dimensional K algebra. The finite dimensional K algebras were the one dualizable K algebras, and I've baked into my assumption that C is dualizable as a one category. So actually, that's another babushka principle that I started my definition of C by asking that it was one dualizable according to my previous. Good question. Okay, so bird tense. So we're talking about two-dimensional things, but it's a four category. And this was actually why we revisited the DSPS stuff. So one, I'll just say it again, every BTC is two dualizable. This is this William-Scheinbauer thing that I already mentioned, topology. Two, every CP rigid braided tensor category is three dualizable. Okay, so this unlocks what are called skein modules, character stacks. Witten theory. So those are all different invariants of three manifolds that people had defined, but there was no guess how to extend. Well, there were guesses, but there was not a construction. Well, Evan Walker told us very clearly what to do, and then there was 20 years of catching up with him, how to construct these things going down, and you get that from this result. So this was in maybe with missing people. If you want, you maybe not be surprised that every braided fusion category is four dualizable. Okay, every braided fusion category is four dualizable. But again, the reason I keep harping on this question about unitarity is the following result. So the way I've been going, you might think that the only way you could hope to be fully dualizable is if you're semi-simple and finite at the top level. That's how it worked for algebras, and that's how it worked for tensor categories. You had to be semi-simple and finite. But here's a result. So if a braided tensor category, call it script A, so it's a braided tensor category, is non-degenerate, is finite and non-degenerate, then A is invertible. Invertible. I'll say what that means, and I'll say why it's worth noting. Okay, so invertible, so dualizable was the requirement that you have duals and adjoints. Exist. And invertible is the fact that they're all isomorphisms. So what I mean by that, for instance, is that a vector space is dualizable if V dual tensor V has a map to the unit called the evaluation with some properties. It's invertible that this is an isomorphism, which is to say that V is one-dimensional. I was about to write if V equals C, but that would have been a mistake. That would have clouded my whole point. Being invertible as a vector space does not exactly mean, it does mean that you're isomorphic to C, but the whole point of this business is that you're not canonically isomorphic to C. And this failure to be canonically isomorphic to C, the difference between being isomorphic to C, but not canonically so, this is the anomaly. This is the source of all anomalies in TQFT. So this is a picture explained to the world by Fried Telemann in around, I don't know, 2008 or so. Not in this example, but more than. So we're interested in invertible objects, but which are not canonically invertible. So we've heard a lot of talk about invertible field theories and so on. I should stop in like 5 or 10 minutes, is that right? Where's the organizer? Yeah? In my notes, I had planned to to spell out a little bit more detail about this statement, but I think what I'd rather do is spend the last few minutes explaining some applications and some work of 2 of my PhD students, which I will discuss in detail on Friday's lecture. I wish I hadn't erased that. So here's an idea of Kevin Walker. I forgot my cartoon. So we got to mountain number 4. Graded tensor categories are a 4 category. And I forgot to say that there's a name for the invariants, the TFTs that you get in this construction. They have a name and it's called Crane-Yetter. So the Crane-Yetter TQFT was famously constructed by Crane and Yetter. And it was done in this top-down way. They guessed the formulas at the top dimension. There it necessarily only depends on the signature and the Euler characteristic. And then they tried to build down. And they got this invertible field theory they called Crane-Yetter. But if you remember on the cartoon, we were not supposed to keep going. We were supposed to sit and watch the sunset. And as we look back, we remembered something, which was that there was this thing called Witten-Reshetik and Turayev theory, which is probably the theory that many of you care about more than any of the stuff I've said. Witten-Reshetik and Turayev is like the thing attached to quantum groups and, conformal field theory and all this stuff. And when we first approached it as a 3D theory, it's shrouded in mystery because it's not fully extended. And the whole game that we're trying to play is study things as fully extended TQFTs. And we also remember about WRT, so it's not fully extended, or not always fully extended. It's a sort of derivative of a physical theory called Chern-Simons. And Chern-Simons has an anomaly. And the anomaly in Chern-Simons basically comes from the fact that when we write e to the I e to the ISF integral over the fields, we like to think that to do topology, we like to think that S of F is a well-defined number. And classically it would be, but what we find when we quantize is that this is only a number mod z. 2 pi, I don't know, 2 pi z, something like that. And so what mathematicians have done is they sort of ran with this, sorry, I just said, sorry, I should have said L of f. Apologies. L of f. And L of f is the integral over the manifold of S. Now I'm getting myself lost. I'm going to... You gotta delete that. The point is that this thing that we're integrating over, mathematicians like to grab onto it and think of it as a number, and that's like our Chern-Simons invariant, but it's only defined mod z, that's the anomaly, but we don't actually care because we're going to integrate it against this. So the physicists are aware of this and have a way to treat it, but that fact that it's only defined mod z, it keeps us from having a fully extended theory. Okay. But there's a beautiful suggestion of Kevin Walker, and it was made somewhat more precise as a conjecture by Fried and Telemann, which is that the 4D Crane-Yetter theory attached to a modular tensor category is the anomaly for the Witten-Reshetikhin-Triav theory. So let me try to spell out what that expectation means, and then I will sketch. So a partial step in this direction. So without the very important question of orientability. Without orientability, but just checking the sort of framed component of the statement, that is a result of Ben Hayun, who's here. And I'll go over some of the proof on Friday. But the rough idea is that what we were doing wrong all these years, and people knew this, but just trying to be dramatic here. We were trying to think of this as a number, but it's not a number. Instead, it's an element of a vector space, and that vector space is the vector space that you get, the vector space of states in the Crane-Yetter theory attached to that same 3 manifold. The fact that Crane-Yetter is invertible means that this thing is, so it's not there, it's rather there, and this isomorphism is non-canonical. So the expectation is that Crane-Yetter is well-defined as an anomalous field theory. And we can make this precise, and so the sort of theorem of Ben, which I should say this, a lot of people made various conjectures in this direction. I won't try to name them all here. The theorem is if we look in the arrow category, so there's this 4 category of braided tensor categories, and from that you can construct a 3 category of arrows. And I was humiliated when Ben started working on this because I didn't understand what this category of arrows was, and it turned out it was much simpler than I thought. So I think so it's a 3 category of arrows. It was constructed by Johnson, Fried, and Scheinbauer. And what is remarkable about this three category of arrows is it's easier than what you might be thinking if you've been following this story about dualizability. Because, okay, if I have an arrow, so what does an arrow mean? I have an object in the 4 category, I have another object in the 4 category, and I have F between them. Okay, fine. Now you would expect, so okay, and I just told you they form a 3 category, there's some symmetric monodal structure on there. What you would expect is that dualizability of F in the arrow category would basically be if and only if F has its adjoints. It's not true, it turns out it's only a one-way direction. Okay, so that's the first observation. And the other thing to say is that this thing is simpler than it looks. So if I have one F and I have another one, G, okay, the first point is that unlike in the usual mantra of higher categories, I can bring these two things together without the source and target having to be the same. So I can have another Z and another W, and I can tensor those together. And you just do the kind of obvious thing. You just take X tensor Z, mapping by F tensor G to Y tensor W. Okay. And actually, if we had read the Fried-Telemann picture better, this would make perfect sense because you're trying to define something in the bulk. You've got Crane-Yutter here, and you've got Witten-Reshetikhin-Sharayev here, and because it's sitting in the bulk, you don't have to ever bend arrows backwards. You don't have to do all the manipulation that you get from the Cobordism hypothesis. Everything is only one direction. You're just trying to put this thing at the boundary, and you don't have to be able to do the kinds of operations that you think. Basically, following the same sort of babushka principle, Ben checks dualizability in this category. And let me just finish by saying the surprise, the Easter egg. Remember I said that you need to be non-degenerate. Being an MTC, modular tensor category, that implies non-degenerate. I didn't tell you the full definition, but it implies non-degenerate. But notice that I did not ask for semi-simplicity here. So there are invertible 4D theories whose underlying category is not only, so they're invertible, in particular they're 4-dualizable, but the underlying category is not semi-simple. That's the main thing I want to emphasize. And so what you can do is you can look at the unit in Burr tense. You can map to your favorite MTC. And you can ask the dualizability without the semi-simplicity assumption. And the claim is that this is, it's all but 3-dualizable. I'm coining that phrase too. All but 3-dualizable is sometimes called non-compact theory, which means that you can evaluate this on any 3 manifold you like as long as you delete one point. So you just don't have the 3 handles, but you have everything else. Ben and a few other of us are working on constructing non-semi-simple WRT theories sort of from the ground up using this. What's up there?
So for this arrow, is it checked for A as a regular module category,
Yes,
or for more general also module category?
So every A, so yeah, I've just making A act on itself on the right and have the unit act on the left. But remember that, just to be careful, that that's as a morphism in the 4 category. So there's sort of 2 levels down from what you might naively mean. So this is A as a central algebra. Oh, but yes.
Right. But a different module category would also produce some relative theory to that, right? To bring together.
Well, that's a good point. I don't know, Ben, what do you think?
Yes, if it's very simple, it's induced by a braided monoidal functor, then the proof applies. But if you want more interesting stuff, it's much more difficult.
Yeah, so thank you, Ben. So here you're right that the structure is just as a 1 morphism and it's the regular one, but indeed, as Ben was reminding us in his proof, to make the computations more manageable, you use that, although I just insisted that this is something more fancy, in fact, it's induced by something more elementary, so you can just work through the adjoints. But I don't think that's a real, I don't see that as like a fundamental error, you just didn't work hard enough.
It's just for the proof, it's not for the duality.
Did you say that for just for tens that the CP rigidity that completely characterizes dualizability via this Barbeck argument, or is it doesn't?
I didn't quite claim that it fully characterizes, and I don't think that's quite true. I think, I mean, it can't be quite true because you can easily cook up an example of something which is CP rigid, therefore dualizable, but which is Morita equivalent to something stupid. Like you take your CP rigid thing and you add it to itself. You make it too big to still be CP rigid, but it's still but it's Morita equivalent to the thing you started with. So CP rigid is a bit of a crutch, but it is what is satisfied by all examples.
Is that actually also true for things like characters stacks? Because I think like quasi-coherent sheaves on non-affine varieties will rarely be projectively generated as a
That's true. That's a good point. So here, that's why I said smooth. Smooth algebraic varieties, just to avoid that sort of thing. But the other example that we care about is BG, the classifying stack, and that is a perfect stack. So it's good enough. So for character varieties, character stacks, you just want the value of the point to be a perfect stack, and that's the thing that Bentley Francis Handler used to do the character theory.
But that still seems as compactly generated, not projected.
Well, no, you're mixing. So in the derived world, you talk about compact generation, and in the abelian world, you talk about compact projective generation. But the abelian category, G, is certainly generated by compact projective. It's semi-simple with infinitely many simples. Yeah.
So in the derived world, you're happy with just compact generators?
I'm not happy with any of that stuff, but some people are happy with that.
You said this is without orientability. Do you have an expectancy for the orientability? Because I would have expected an MTC to already give me
Right. So thanks. So I talked about, I went through, thank you. So the question was, okay, fine, I've just been doing dualizability checks, but I just stopped talking about orientability. The issue is, I won't say anything definitive here, but I'll just advertise some lecture notes by Chris Schomer-Priest. Which is about their joint work by the same authors, Douglas, Schomer-Priest, and Snyder, which is about, so you look at BSON as a homotopy type. So if I had another couple lectures, I would have liked to talk about this. It is very beautiful. So BSO2 had this cell structure where we just had an E0, an E2, an E4, and so on. It was really nice. But if you tried BSO3, oh gosh, I don't even remember. I think it has E0 and then E2, and then there's an E3, but the way that this clutches is the hop map, the hop vibration. It's got an E4, which is the belt trick. So it's got a bunch of, it gets really hairy. And in particular, you get a sort of traffic jam in low dimension here of lots of complicated stuff. Whereas the way that you were able to move in with SO2 was that there was not very much stuff, and the stuff that there was, you could ignore because you're only doing 2D TFT. But if you try to follow that technique for three-dimensional orientations, then you have to deal with two compounding factors. First, this is more complicated, and secondly, your cutoff is higher. So unfortunately, BSON has lovely cohomology ring. It's lovely if you want to map to it. It's a classifying space. It wants you to map to it. What it doesn't want you to do is map out of it. And when you try to map out of it, you have to deal with all this stuff. But these people are brave. And what they've done is they've worked out algebraically everything in these dimensions. And they've given you a sort of presentation in terms of this CW structure. And then they've conjectured how this maps into Bertets and what all the structures look like. And then to answer your question, yeah, the conjecture is that the BSON action does a bunch of sort of things that look like ribbon twists. And just like we saw this loop-de-loop, that's going to look like some actual ribbon twist. And that a ribbon structure is the thing that trivializes it. I guess you probably know that expectation. Right. One of the things that I was also happy about with this three category of arrows is that at least you can go down one dimension less. So my original proposal to Ben, you needed to understand the SO4 structure on the 4 category and then sort of go back down to BSO3, and you don't need to do that. You can just talk about the 3 type.
If there's no further question, let's take a 3-minute break.
Okay, so it was pointed out to me the other day over dinner that I made an error in stating the fixed point structure. So you can see my my whiteboard, yes? Can everyone's, yeah, okay, great. So it's pointed out that I made an error in stating the fixed point structure for in the case of alg 1. So I thought I would take the opportunity to fix that error, and then also and then just go through briefly what is known, what is expected in the other cases. So okay, so right, the error that I made, I'll just recap it this way. So remember we had to say where the 2-cell E2 went. And I gave a formula for a bimodule, but the bimodule I gave was canonically trivialized. This was pointed out to me. What I meant to say is this. So what E2 does, it sends the regular AA bimodule to the dual vector space. That inherits also an AA bimodule structure, but now the left and right actions get swapped as usual. And then trivializing this is the notion of a symmetric Frobenius algebra. Okay, so that's a correction. We can look at so alg 1 in categories, fully dualizable. We saw that those at least contain the fusion categories, and there's an SO2 action there. well, in fact, let me be more precise. Those contain just the, what I said is true, but those contain the, no, okay. Never mind. Let me not state the most general thing. So those contain the fusion categories. And then there I wrote down the correct formula. At least nobody has corrected me yet. So we're going to still look at the SO2 structure. Now there's also an SO3 structure we'll come back to. But just looking at the SO2 structure, we see that E2 maps to the category, but now the regular bimodule category maps to itself, twisting by the double dual functor. So I gave the same formula the other day for vector spaces, but it wasn't quite true. Okay, and so then a trivialization of this would be what you could maybe call a weak pivotal structure. A pivotal structure would mean that the double dual functor, the functor of taking two duals, is equivalent to the identity functor. And a weak pivotal structure says that you conjugate possibly by a canonical invertible element. Object. Okay, so as far as I know, this is due to Douglas, Symmetries, and Snyder. Okay, but now here's something kind of nice. In fact, so as we said, so we have SO2 action, but we also have the SO3 action. So when we look at BSO2, it maps to BSO3. And the two-cell E2, maps to another cell called E2. Now this is the two-cell that I've listed here. This is part of a cell structure for BSO3, but now there's a three-cell E3, and the way that it attaches onto E0 union E2 implies that pi 1 of so pi 1 of SO2, which is pi 2 of BSO2, that's Z. The way that this attaching map goes, pi 1 of SO3, which is pi 2 of BSO3, that's Z mod 2, and then the map here, which is the map here, is the map here, canonical projection. And actually that's kind of a cool observation, because what it says is that in any, so Radford's theorem, which is known without this trick, what it says is that in any fusion category, if I take the double dual functor, which I always have in a fusion category, and I do it twice, so that is if I take the quadratic dual, this is isomorphic to the identity functor in a monoidal way. And so in particular that implies that this d squared, this d, this canonical d, is the identity. The remarkable thing is that from this DSPS picture you get this for free just from the fact that this z becomes a z mod 2. So that's kind of fun. Right, let me just mention there's a conjecture. So that means that i.e. every fusion category has, how do I want to say this? So let me just state a conjecture, which is very close to what I've said. every fusion category admits a pivotal structure. As far as I know, this is still open, and if that's true, it's been open for a long time, and it's pretty tantalizing because you get a square of a pivotal structure for free. But constructing pivotal structures in some canonical way is not known. Okay, so now let me go on to the higher dimensions, and I'm just going to state expectations. And I think that some of these expectations are in the process of being proven by various people, especially Douglas, Symmetries, and Snyder, but I think also Ayala and Francis, working in a different context. So let's look at now alg 2 in categories. So we're looking at braided tensor categories. Well, that, as I've said it there, that's just the definition. So in particular, the fully dualizable, or sorry, the three dualizable objects are just CP rigid braided tensor categories. And this has an action now of SO3. These are three dualizable. Okay, so some nice stuff happens. Okay, so you can observe a few things. So SO2 times the identity, and the identity times SO2, those are both subgroups of SO3. And if we have a rigid braided tensor category, we can either regard it as just an E2 algebra and do topology, or we can regard it as a rigid tensor category and do some sort of tensor algebra, and we get two different things. So when we trivialize this action, let's say that's the one where we lean on the algebra structure. What we get is a pivotal structure. And we get a Radford isomorphism. Okay, and we get that Radford isomorphism not because we're using the finiteness now. So to get the Radford isomorphism over here, we needed the SO3 action. So the Radford isomorphism comes from the existence of the SO3 action, which reduces this Z to a Z mod 2. Over here, we needed the category to be a fusion category, to be nice and small so that we could do this. But over here, the braided tensor categories are allowed to be perfectly large, but because they sit inside this SO3 action, because they sit inside this three dualizable category that now uses the braiding, we can trivialize the quadratic dual. But as expected, it uses the braided, using the braiding. So I'll try to draw it something like you go like this, and then you go like this, and that's a monoidal map from there to, if I haven't got it wrong. No, that one looks, is that one? No, that, let me not try to fix it now, but let's check these crossings. So there's an ordering of those crossings. I won't try to fix it now. That makes this monoidal. I think the one that I drew is just the thing in its inverse. So I think I wanted to fix those crossings. Okay, so that's a nice fact. And then another fact is that if we look at the other trivialization, we trivialize this other copy of SO2 sitting inside there, this gives us a balancing. And remember, a balancing is, different ways to say it, but we're looking for theta, an automorphism of the identity functor on our tensor category, braided tensor category, such that if I do theta on V tensor W, that's theta V tensor theta W composed with the double braiding. Okay, and this balancing actually comes, in our picture, this balancing comes very naturally if we think about disk 2. So I only talked about framed disks, but there's also a notion of oriented disks. And the picture that you should have in mind, of course, is here was our picture for disk 1 framed. And if we want oriented disks, then what we want is there's an action of SO2 on disk 1 framed, which commutes with everything, and the action is just given by rotation. Of each disk. And of course, if I rotate that disk, so if I rotate that disk by 2 pi, what's going to happen is that, first of all, the 2 individual disks are going to do a full rotation, so do that twice. Not just a swap, but a full rotation. And also inside, they're going to do a full rotation. So that's this formula. Okay. I'll just pause there before I go on, so everybody sees the picture. Oh, but I forgot to say what is expected over here in the fusion case. So we talked about the SO2 action, and we started talking about the SO3 action, but there are more cells. So I mentioned that BSO3 has a 3 cell and a 4 cell. Now when I say it has a 3 cell and it has a 4 cell, I mean, that's not well defined. It's a homotopy type. You can try to write down a CW complex for it, and what I mean is that Douglas Schomer-Pries and Snyder proposed a sort of notion of like a minimal workable CW complex, and their minimal workable one requires you to have some 3 cells and some 4 cells, and we saw that the 3 cell gave us this Z mod 2. The 4 cell gives you that you need a spherical structure. And the fact that you should need a spherical structure on your fusion category is natural. The word spherical means that you can evaluate on a 3 sphere. So that's natural. Okay, so right, and so here I'll just be brief, and I'll just say the expectation is that the full BSO3 trivialization equals a ribbon structure. But this is not so obvious, because when you look at the cell structure, there are some cells that are not accounted for in the nice way that they get accounted for over here. There's some cells that appear to apply an identity, which we don't know what that identity is. So there has to be there needs to be some more work from what was announced by DSPS many years ago. But my understanding is that they're in the process of doing that. Okay. Okay. So I want to jump gears a bit and get back to discussing this Crane-Yetter and WRT story. But let me pause to see if there are any questions. No? Okay. So, so here's a sort of Crane-Yetter.
Can you write a little bit bigger?
Write a bit bigger, okay. Is that better? Even bigger. Okay, I'll try to write even bigger, sorry. Okay, so Crane-Yetter paradox. Okay, so, right. So, classic work of, I want to say, Madsen-Tillman. Says that any invertible 4D TFT depends only on the 4 manifold. So the number depends only on the 4 manifold up to homotopy. And in particular, it depends only on the signature of M and the Euler characteristic of M. And now for framed 4 manifolds, these are both trivial. So that would seem to say that studying Crane-Yetter as a frame TFT is sort of a pointless thing to do because it can only produce completely trivial invariants of 4 manifolds. However, let me assert there do exist non-trivial yet invertible 4D framed TFTs. So let me not use the Q here. And these come from objects, invertible objects of this 4 category. And so how do we square that? Well, the point is that that Crane-Yetter only comes alive in lower dimensions, which is of course just another way of saying that we should regard it as an anomaly for an interesting 3D TFT. Okay, so last time I sketched that we can construct, so following proposal first by Kevin Walker and then formulated in this language by Fried and Telemann, we can construct the WRT invariant as a map from the unit, so the trivial theory, to our braided tensor category A, which is just the regular module, and this is all taking place in an arrow category. Okay. So this notion of this arrow category, oops. So this is subtle, and I just wanted to give you a quick sense of the subtlety by sharing with you. So this is the paper. Can you see my screen? Are you still only seeing the? Do you see a browser, or are you still only seeing? It looks like you're only seeing my notepad. Hold on, let me reshare. Okay, so this is the paper of Theo Johnson-Fried and Claudia Scheinbauer, where they introduce the notion that we need I think I said before that you need this even to make some of the previous things I said make sense. In particular, Burr tense depends on this notion of even higher Morita categories. But I want to take you to just show you. Where is it? Sorry. Yeah. So in this notion of arrow category, there's okay. So our objects in the arrow category are these are one morphisms between two objects. So that's like, you should imagine the unit is here and your favorite braided tensor category is here. But then you want to spell out some higher coherences, and it turns out that there are two natural things you can do, but they're both a little bit puzzling. So there's one called lax and one called oplax. And I won't really try to talk you through all of the points here, but I'll just say that the oplax one is highlighted by the fact that, so you see the difference is you have this you have some commuting diagram, or some would-be commuting diagram of arrows. So you've got your functor, you can apply it to an arrow. So that's F and G. And you want to say, what is the notion of a morphism between two arrows? And one thing that might seem natural is that you would have some data pointing down here, eta from F of B1 to G of B1, and so on. So you have that in both cases. That's to be expected. But then you get this natural commutative diagram, and then the question is, how do you want to make this thing commute? You can either make it commute by pointing along this composition, or this is the same diagram flipped on its axis, and you can make it commute this way. So yeah, we have to use this one called oplax, basically the thing to notice is that the oplax one, it has the morphism going sort of in the same direction as the arrow. So it's going from, here's the arrow F of B, here's the arrow G of B, and you've got a morphism pointing that way. And then when you look at the notion of two morphisms in the oplax case, you see that all the arrows are pointing in the same direction. So it turns out when we want to talk about anomalies, we want to sort of imagine that G is our interesting theory, and everything is kind of flowing out of the trivial theory, and that's going to be our structure. Okay, so I just wanted to give you a quick glimpse of that and warn you that it's a bit technical.
What changes when you choose lax instead of oplax?
Yeah, that's a good question. I mean, thank you. So the question is, what changes if you choose lax versus oplax? To be honest, looking at Theo and Claudia's paper, I wouldn't have known which one to use. I should have said that if either of those maps, that in either the lax case or the oplax case, if they happen to be an isomorphism, then of course everything is. Then you get this notion of a strong morphism, and then you can stop worrying. The issue is just that when you go to do examples in categories, you see consistently that the categories have they satisfy the and in fact factorization homology. It's not even about categories; it's about factorization homology. When we map the trivial, so when we map the trivial theory into the category, we're sending the unit n. And the reason why we need this oplax notion from that point of view is that we will always have the sort of the trivial object, which is like the structure sheaf or the empty skein, or there's always going to be some distinguished thing which corresponds to the empty set, but it's not going to compose like an equivalence. It's only going to it's going to come along for the ride, but not be an equivalence. And when you go and check, if you're presented these two options, you can just check that one works and one doesn't. I wish I could say something more intelligent. In fact, if Claudia is there and wants to say, she could. Okay, I guess she doesn't.
Okay, good.
Okay, so I'll share my screen again. Back to the, where did it go? Okay. Okay, so actually this paper, it's technical, but it was really a big step forward for the whole JFS, excuse me. It's technical, but it was a huge step forward. Okay, and so, right, so in the semi-simple case, executing the above already followed from our previous work, basically because we showed that this is, so the question is, you have this arrow category, so the question is, given this arrow category, what are the dualizable objects? What are the dualizable arrows? And so if you work, so now there's actually these three settings. So if you work with the most naive notion of strong, then this at least contains braided fusion categories. But the question that was interesting, which was answered by Ben, is that if you work with oplax, then, okay, so, sorry, what do I mean to say? So here, we take fully dualizable, and then you get the braided fusion categories. Here, we want to take all but dualizable. And that contains, that can contain non-semi-simple finite braided tensor categories. And remember, all but dualizable just means that we don't have, that we can't add three handles. So these correspond to open TFTs, or non-compact. Okay. Right, so let me just mention in passing that Reuter and Walker in a seminar called the UQSL seminar announced. So the reason why you don't have three handles, it turns out, is if you look at the three sphere and you look at the filling of that by the four ball, that's supposed to be one of your adjunction data, and if you do this naively, rather than being a well-defined adjoint, this is just zero. This is the zero map. And so some of you will know this as the degeneracy of traces. So there's a lot of literature. So there's something called the modified trace, where you basically, this trace is degenerate, but it's degenerate in such a way that you can just renormalize it. You get something called the modified trace. And then this gives you some non-semi-simple WRT invariants. So a lot of people have worked on this. So there's, let's see, Blanchet. I guess the paper that comes to mind is Blanchet, Gear, Blanchet, Costantino, Gear, and I'm really sorry if I misspell this, Miran. So BCGP. So what these folks did is they knew this fact about the degeneracy of the traces, and they invented this notion of modified traces, and then they bootstrapped the sort of traditional WRT construction that's not fully dualizable to construct. So that they constructed non-semi-simple WRT invariants. Okay. So that work already existed, and what we're trying to do in this discussion is to sort of reinterpret it as something fully dualizable and using anomalies and such. Okay. All right. So. Okay. So let me now explain something new. So that was largely just recapping what we had explained in detail. What I said at the end. So, there's a new layer I want to add. Okay, so everyone knows that the WRT invariant on the math side is just the same as what people call Chern-Simons on the physics side. And as is common of most things that everyone knows, this is not true. What's more accurate to say is that the WRT theory on the math side corresponds to the Chern-Simons theory on the physics side, but only in the local neighborhood of the trivial local system. Like even in Witten's proof and in many mathematical approaches to the Witten-Reshetikhin triad invariants from Chern-Simons, you just look at the formal neighborhood of the critical locus. So this is the sorry, not the critical locus. This is the formal neighborhood of the trivial local system. And this is more correct. Is there a question? No, okay. Okay, so so the question I would like to ask, and which is being answered, is can we do better? And so what we're going to do is we're going to define a WRT theory on the math side. So it's sort of a varying WRT theory on the math side, which is going to correspond, well, okay, so it's still not going to give you the full rich structure of Chern-Simons theory, but what at least we'll be able to do is we'll be able to vary it along the entire critical locus of the Chern-Simons functional, and this critical locus is what's called the character stack. And so the character stack, given some group G and some manifold M, this is the moduli space of flat connections. So we saw this before, so let me write it like this. So M, we have some principal bundle, we have a group G, and we have a connection. So we saw this all the way back in the finite group case. This needs to have a group action G, and we want that E mod G equals M. So this is just me spelling out what a principal G bundle is. And then there's also this data of a connection. But actually, let me give a more pedestrian definition of the character variety. We just look at representations of pi 1 of our manifold mapping to the group G, and we can consider those up to conjugation, and then we want to treat this as a stack. Okay, so that's that. So what we're going to do is we're going to define a version of the Chern-Simons or sorry, we're going to define a version of this one. Chern-Simons already kind of lives over the critical locus. We're going to define a version of the WRT theory which varies in this way. And I think it's going to help resolve some confusions and maybe lead to some new invariants. Okay, so right, I'm mindful of time, so let me try to speed up a little bit. So the basic algebra, so I realize I haven't done a single example in algebra this entire time, so let's do one. So Lustig's divided powers quantum group. So this is just a lovely algebraic object. If you haven't seen this, just go spend a week reading, well, I don't know, Lustig's book is hard to read, but still it's worth looking into. So it's an algebra over Z adjoin QQ inverse. And it's generated in the following way. So it's going to be a variant of the presentation of the quantum group you've seen before. So it has generators called KR, ER, and FR, and these are, here the R is in Z, and here the R's are in Z greater than or equal to 0. Okay, and what you should think in the formulas that I'm going to give you is you should think that e to the r is the usual power e to the r divided by the quantum r factorial, where quantum r is like q to the r minus q to the minus r over q minus 1 is this number that or over q minus q inverse is this number that becomes r when q equals 1. Okay. So what you should think is when I put a parentheses around a power, it means that I'm just going to renormalize it by this thing. And so that leads us, for instance, to the following relations. So e to the m times e to the n equals e to the m plus n. But now we need to sort out these denominators, and we get a nice expression. We get a choose function. So m plus n choose m. Okay. And the point is that if we take, so let me call this, I'll just call it UQG. If we take UQG and we tensor over CQQ inverse with, say, rational functions in Q, then this is just isomorphic to the usual quantum group. And in fact, what I've done is I've given you an embedding of UQG, this particular form, inside there when I gave these formulas. So this is what's called an integral form. Okay. But now what we want to do is we want to not embed it inside. We don't want to do that. What instead we want to do is take this same thing and tensor it over ZQQ inverse. Okay, there's various things we could do here, but let's take Q, let's say Q of epsilon, where epsilon is some nth root of unity. In other words, all I'm saying is we're gonna impose the relation that Q to the L equals 1. Okay. All right. So if we do that, I want to point out something very, very cool. So e to the L. So let's take the normal nth power of e. So that's e times e L times. Well, by definition, that's L factorial times e to the divided powers L. But that's 0 because L factorial vanishes. That's actually the whole point of this construction. And so what it means is that the small quantum group, so this is the thing where e to the L equals f to the L equals 0, and k to the L equals 1. This is the small quantum group. this sits inside the big quantum group. And here I'm specializing q to the L equals 1, and I'm not going to keep writing that. And now, even more remarkably than that, what Lustig showed, if I take, so if I take UQG, and I quotient by, okay, I have the augmentation, little uq, mapping to the ground field that just sends E, F, and K, E and F to 0, and K goes to 1. If I quotient by this ideal, so I make it into a two-sided ideal and I quotient, what I get is a finite extension of U, and U here is the classical universal enveloping algebra. The classical one, like the one with the usual Serre generators. So if I kill those E's and F's, then all I'm left with is the E to the L's, where, or maybe I'll say E to the N times L, where L is the order of my root of unity. And it turns out that modulo the lower stuff, you can really think of this as just E to the L raised to the N. And if you send E to the L to the classical generator E, then this defines an isomorphism. There's a finite extension, which I won't worry about. Okay, so let me paraphrase what's happened here. So colloquially, what we've done is we've said that the Lustig's large quantum group has a quotient, which is the classical enveloping algebra, and it has a sub, which is UQ. So if we were thinking of these as groups, I might be inclined to think of this as the quantum group, this is the classical group, and this is some finite extension gamma, so Q. Okay. UQG, Lustig's quantum group, has an R matrix. And in fact, its R matrix is the same R matrix for the small quantum group, just interpreted this way. What we do is we take the usual formula for the R matrix, and so you may have seen this before. It's like Q to the, let's say, H tensor H over 2 times the sum K equals 0 to infinity of, now what you usually write is E tensor F raised to the kth power, divided by quantum K factorial. You may have seen that for SL2, for instance. The beautiful thing is if we rewrite that in terms of the divided powers, then we still have this funny factor. Let's not worry about that. But now this becomes the sum K equals 0 to infinity. Now, you see I've only divided by 1 power of K factorial, but if I rewrite this in terms of the divided powers operators, then I actually get an extra factor in the numerator. And then we see that this only keeps the first view, keeps only the finitely many terms. So this quantum group, it has an R matrix. There's not even a completed R matrix, just a finite sum. And moreover, here's the beautiful thing: if V is a rep of G, a classical representation, I have the map pi, which goes from UQG to U, and I can pull back V. This is transparent. Because remember that this homomorphism pi was obtained by just insisting that all the E's and F's act as 0 and all the K's act as 1. well, that means that R restricted to pi star of V is just 1, which is to say that if I take any representation W and I double braid it by pi star of V, then I just get the identity. So this is the notion of transparent. Okay. I realize I'm conscious I'm running short on time. Oh, okay, we have a bit of time. Okay. So what I've just done is I've just told you that rep G maps to the Muger center of rep QG. And I've also told you that if I take rep QG and I tensor it over rep G with vect, where here vect is the fiber functor, this is the same as representations of little uqg. Okay, that's just a really beautiful fact. Now, for the people doing algebraic geometry or familiar with the language of algebraic geometry, what I'm saying is that there's a space, there's an algebraic stack called BG. It's an algebraic stack, perfect. So it's a stack, but it behaves as if it were smooth. And it only has one point. One absolute point, but it has lots of sort of stacky stuff. And what I'm saying is that rep QG is a sheaf, so this is a sheaf of E2 algebras. It's a sheaf of E2 algebras living over this whole thing, and its fiber at the point, at the absolute point, right here, is representations of the small quantum group. Okay. So that's a lovely picture. And so now, so was there a question or just a cough? Okay. 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 So now, how are we going to interpret this? So, so the idea. So I want to make sure to attribute this. So this is conversations with David Ben-Zvi and Pavel Safronov. Wouldn't usually attribute an idea, but I want to make sure to not imply that this is either my idea or Patrick's idea. The idea is that this invertibility, that this is an invertible sheaf, and that this implies invertibility all the way up. And this was proven in a very nice result. So this is by my PhD student, Patrick Connier. So what we do is we regard rep QG not just as an E2 algebra, but we regard it as an endomorphism of rep G in the 5 category of symmetric tensor categories. So that's a construction. I'll remind you how to think about this. His theorem is It's not just an endomorphism, it's an automorphism. So the fact that rep of little uq was invertible in Burr tense, now we upgrade this to the fact that rep qg is relative invertible in sim tense. Okay, let me just remind you this 5 category. So remember, we were happy thinking about braided tensor categories as things living on a line, or on a plane. That's rep Q. And I'm just saying that you can put the classical group rep G and the 3D bulk, that's 2D, and that's 3D. But really we're supposed to remember that there's 2 category numbered, there's 2 dimensions coming from working with categories. So really this is a 5D sort of what you call a semi-classical gauge theory, just like the sort of data that you would study in classical gauge theory, and it's acting on the 4D theory. And so let me just, in the last few minutes, say the kinds of things that you get. So in usual, so we need to return to Crane-Yetter. So in usual Crane-Yetter, for instance, Z of some 3 manifold would be a vector space. In relative Crane-Yetter, Z of a 3 manifold is not in a vector space, but it's rather a line bundle. Or what? Yeah. So, well, first of all, it's a vector bundle on the character stack of M. But in fact, by Patrick's result, it's better than that. It's a line bundle. And so the remarkable thing is if you try to go back this way, the way that you go back is by taking global sections of the line bundle. And you notice something, that a line bundle means it has one-dimensional fibers everywhere. So that's kind of nice and invertible. But when you go back and you take global sections, then that thing can have infinite dimension. So here it's sort of one-dimensional fibers. And yet when we go back, we can get things that are infinite dimensional. Okay. Yeah, okay. I'll just wrap up here quickly. So likewise, Z of a surface in Crane-Yetter is a category. And here, Z of a surface is actually a sheaf of categories. It's also known as a gerb. So more precisely, I shouldn't write sheaf, I should write gerb of categories. And this actually recovers some very well-known work. So Bonahan and Wang made this famous conjecture called the unicity conjecture, which basically tells you that skein algebras at q to the L equals 1 have sort of unique correspondence. So just have a correspondence between their irreps. So the skein algebras are non-commutative, but there's a correspondence between their irreps and points of the character variety of the surface. And this is just, and so this sort of conjecture was attacked by various people. So Roman, Kanya Bartaszynska, and Tang Lei, and then they showed that this is true generically. And then with Yordan Ganev and Pavlo Safronov, we showed this is true on the smooth locus. And then there was a recent work of Julian Korenman and, oh gosh, does anybody know the collaborator on this?
K-A-R-U-O.
K-A-R-A-U?
U-O.
I'm sorry, I can't actually hear, but apologies. So there was a recent paper that nailed this down precisely. But the point is that that this kind of unicity that we were aiming for here is really should just be thought of as a manifestation of this invertibility. And then the last thing that I'll say is that, so remember, WRT is supposed to come from the anomaly Crane-Yetter-Kaufman theory, and the expectation is that we now need to look, okay, so we took sim-tense, and we had to look in its arrow category. That's where Kinnear's work was. On the other hand, we had to look at Burr tense and look at its arrow category. That's where Hayun's work was. And now we need to do a sort of push out. To get WRT, which is to say we should look at sem tense. We should look at its arrow category and use Kinnear's work. And then we should look at its arrow category and use Hayun's work. And so this arrow category we've already seen, that's rep Q. And then here what we're going to use is just the fact that we have the structure sheaf to any line bundle. And that is going to give us the non-semi-simple WRT. And so the kind of data that we get then is non-semi-simple WRT, so varying non-semi-simple WRT. So instead of getting a number attached to a 3-manifold, instead of getting a number that is like you would in ordinary WRT, what we're going to get instead is a function, polynomial function on the character variety of the 3-manifold. And we should think that the Chern-Simons invariant that we wanted to study, that's ill-defined mathematically, is the integral over the character variety of this number. Thought of as a function. And the point is that this is non-compact. So this is infinite. But by sort of fixing the semi-classical background fields, then we can get something that has all the structure we would have liked. Okay, I apologize for going over time. I'll stop there. Caruo. I was close. Let me fix that.
Are there any questions for Edward?
Yes, maybe we can shout.
Could you speak very loudly? I can just barely hear you.
I have 2 questions.
I think there's a microphone.
Where is the microphone?
It's like this boxy thing.
Oh, wow. Hi, David.
Now I can see you too, Michaela. Go ahead.
I have 2 questions. Hi.
So first question is, it seems that this simply non-semi-simple WRT is to think about it really as a relative field theory, no?
And as a relative theory, that depends on whether the thing is a vector or a line bundle, no?
That's right, yeah.
So is it a vector bundle or a line bundle? The like, first question.
Very good. You mean here?
Yeah.
Yes, yeah, okay, good. Yeah, thank you. So, you're right. So here, yeah, good. So, yeah, as you said, this thing is a line bundle. So the Crane-Yetter-Kaufman invariant of M3 is a line bundle on the character variety. And then the relative invariant is not a function, as I wrote. You're right. The relative invariant is a section of that line bundle. Yeah.
Thinking about infinity, sometimes in physics, where we have to deal with integrals over non-compact things, we make them equivariant. So I know there are some notion of things called omega backgrounds.
Sure.
Space-time, or in these cases, since you have this modular space, we can kind of turn on fugacities over it, and that sometimes allows to make some predictions about some quantity that would be infinite without this at all, and instead they become like kind of computable. So as an example, we can compute some elliptic genera for some sigma models, 2D sigma models on non-compact hyperkähler targets. So is there a notion of equivariance that can help dealing with that invariant?
Yeah, it's a good question. I think, I'm not sure, but I think that sort of, there's one way to think about the sorts of things we're discussing where that's sort of built in the sense that I think you can think of the parameter L. So L is related to the level in Chern-Simons. But really we're also thinking about the parameter psi in Kapustin-Witten twist of n equals 4. And I think that there is a way to think about, so you mentioned omega backgrounds. I think there's a way to think of the, okay, I think this is not known or written about, but let me try and say, so the same structures also appear in 3D n equals 4 theories and their Coulomb branches. So that is the character stack, for instance, is the Coulomb branch of 3D n equals 4 theory for the corresponding surface, say. And basically, I think that the L or the psi is some ratio of omega parameters. So I think you're supposed to think that you have two S1s sitting inside, two commuting S1s sitting inside of SO4, and you get these two parameters. So yeah, I think I'm not sure if that's the kind of answer you're looking for, but I think somehow you might say that this has already done that. That this has already. You might after the fact think that this has already done that, but I need to be careful because I don't really know what this this means. It's just what some people have explained to me how to think about it.
There are no more questions. Let's thank David again and Enrico.